not seeing this. That's surely important. Okay, interesting.
Yeah, we can see it.
You can, yeah, we cannot. That's the issue. Right. Okay, there we can go. Okay, I'll leave the room to João. Hi everyone. So let me see if I can get this on full screen. And you guys tell me if you miss anything. You still see the sharing, right?
Yeah.
Okay, perfect. Okay, so hi everyone. Let me. Do you prefer if I? Yeah, maybe it's better if I say like this. Okay, so hi everyone. My name is João. I'm João Ribeiro. I came here from the University of Lisbon. Our work, this is a partnership between my supervisor. I'm a PhD student in the University of Lisbon, like I said, and our work, Ad Hoc Teamwork under Partial Observability, it was a joint project between us and a master student. So, first and foremost, hopefully most of you know what Ad Hoc Teamwork is. I'm going to lay down the baseline or the main assumptions that are commonly shared between works in Ad Hoc Teamwork. But let me show you why we are working with partial observability, first of all. So I came from a laboratory, which is called the Group of AI for People and Societies. And one of our main areas of research is human-robot interaction. So unlike the usual environments or multi-agent systems where we develop autonomous agents, and working with real robots and humans, one common issue is that you have usually sensors which you use to obtain information of the environment. So there's usually no full observability. So this is why we want to pursue partial observability. So Ad Hoc Teamwork, first and foremost, it studies how autonomous agents can adapt to unforeseen situations and teammates on the fly. That's the simplest definition I can give of the research problem. Usually, most works lay down the following assumptions. The ad hoc agent is not able to coordinate with his teammates, nor communicate. So usually, imagine you go to a different country, you have some issue, you do not speak the language, you have to make do just by observing and see what everyone is doing. However, you assume that your agent may use some prior knowledge. So he may use the previous situations you went to another country, you saw a similar problem. Now he cannot speak, let's say, Chinese, but he already did it in Brazil, for example. So he can now do the same procedure he did in a different country. You can also observe the state of the environment. This is a common assumption. Also, observe the actions of the teammates. In multi-agent systems and simulated environments, you have explicit access to the actions of your teammates. And finally, you can also access reward signals, even though Ad Hoc Teamwork is not reinforcement learning. So, Ad Hoc Teamwork under partial observability. We simply move the assumption or we eliminate the assumption that the agent is able to observe the state of the environment, the actions of the teammates, the reward signals. In this case, the agent can only have prior knowledge and partially observe the environment. So our research question is basically the same. How can autonomous agents adapt to unforeseen situations and teammates on the fly, relying only on partial observations and prior knowledge? So this is where our contribution now comes in hand. The Bayesian online prediction algorithm for Ad Hoc Teamwork under partial observability, or ATPO for short. So how does it work? Very summarized. First of all, we create a library of possible models which represent either the teammates, the goals the teammates are trying to achieve, or even both, a combination of both. This can be either given to the agent, for example, by hand coding the models using Markov decision process, or learning these models in simulated environments where we in fact have access to the actions and the rewards. Afterwards, you then solve each model and you give these solutions to your agents, because the solutions are called optimal policies, which are mappings between the observations or the states and the actions which our agent is able to perform. You then give this library to your agent, and you let it perform ad hoc teamwork. So when performing ad hoc teamwork, how does this process? First of all, you assume your agent is interacting in a multi-agent system with some arbitrary team. We call here the team A, which we represent as a meta agent. So let's say you have multiple teammates. We can represent a single joint action for the teammates as a single index. After interacting with the environment, our agent is only able to observe a partial observation. So is not able to obtain the rewards nor the actions of the teammates, which is something unfeasible to obtain in real world scenarios. We then assign beliefs for each possible model uniformly. Let our agent act upon the environment by performing a weighted sum. We just do away the sum of our probabilities, our belief probabilities versus our optimal policies. And we observe the environment. And then by collecting this evidence, we are able to use it to perform Bayesian inference, as you can see here. So the action of the teammates, which we don't know, and our own action influences how the environment transitions from a given state to a next state. And that next state influences what we observe as a partial observer. And then we update these beliefs using a simple Bayesian update. And using this new information, we can simply repeat the process until the task is considered complete or until a given horizon is established. So you use again the same weighted rule. So to summarize, our approach at PO is a novel approach for ad hoc teamwork under partial observability, as the name suggests, which is capable of adapting to teammates and tasks on the fly without relying on states, actions of the teammates, and reward signals. It only relies on a library of possible knowledge and partial observations. So, before I get into our evaluation, there's only a main challenge, which is how can we compute these probabilities to update our priors? Well, we're currently exploring two strategies. The first one, like I hinted before, is by using Markov decision processes, where we model each model as a partially observable MDP. And in this case, we have access to both the observation probabilities and the transition probabilities, which we can use directly to update the prior. Our second option is to use function approximation and neural networks, for example, recurrent models, to compute these probabilities directly in a supervised structured classification way. So I'm going to show you our current results so far, which is using the POMDPs. So we set up 11 domains with a total of 70 POMDPs, 3 of which can be seen here. And then for each domain, we build a library with an arbitrary number of models, usually 3, 4, in some cases even 32 in some domains. And then we solve each of these POMDPs to obtain the optimal policy using the Perseus algorithm. So regarding baselines, we have 4 main baselines, some others which I'm not going to get into detail here, but from these 4 main baselines, we can consider 2 of them as the best possible performance and the worst possible performance. So this one called value iteration is one which is able to fully observe the environment and get its optimal policy. The other one simply acts randomly. And we evaluate our agent against these 2 baselines, we can see that in all domains, our approach is very effective in solving the tasks assigned. So one question remains, or about, is it able to identify the correct model or the correct teammates? Well, if we look in each domain into our model probabilities and the way the beliefs are evolved over time, we can see that in almost all cases, after a few time steps, like 10 time steps, 8 time steps in some cases, it is able to get a very low entropy and a very high certainty, in this case, on which is the correct model, as you can see here. So, to conclude, I don't want to bore you anymore. So, in this work, we have proposed a novel approach for ad hoc teamwork under partial observability, which is able to assist teammates on the fly without relying on states, actions of the teammates, and reward signals. Only some prior knowledge and partial observations. Our results have shown that our approach was very effective in assisting the teammates on the fly. Thank you so much. This concludes my presentation. I'll now be open to questions.
Thanks. Now, I don't know if we have any questions in the room. Anyone or yeah.
Yeah. Okay, I want to make sure I understood this correctly. So you have like MDP models, right? Maybe some prior distribution of these models. Couldn't you just put these all these models together into a single MDP? With like a higher level belief space over the possible sub MDPs, and then try to just
there's a similar work. There's a similar work which does that, and our way of sorry. So our colleague here is asking if another possible way of doing this work would be to join all models into a single POMDP and then solving it. Well, first of all, by doing that, you are increasing the state and observation space by a lot. So it's easier to solve smaller problems than a really big problem. With POMDPs, the way the solutions work right now is using a class of methods called point-based solvers. And what they do is they try to sample the belief space of the POMDP. We can get into more detail offline if you want. And when they are solving the POMDPs, the larger you have the belief space and the more observations, the longer it takes to solve. For example, some of our models took 11 hours to solve on a really good server. So if you do a single one, I don't have any guesses how long it would take, but I think it would be harder. And the other thing would be that you cannot tell exactly which model, or I did tell with certainty how you can identify the teammates. So in this case, you can say, we've identified the most likely teammates as this model. If you have a single one, you cannot do that. That's on top of my mind, the best explanation I can think of. Yeah. What about you guys?
Anyone else? Or online? I do have one question if no one has questions here. For you?
Yeah. I just wanted to check. So when you like have these different POMDPs, the kind of unless you're including the models of the agents, like the policies.
Of the what? Sorry.
Of the other agents and the.
Yes.
Okay, so that's very clear.
That's a really good question. So your colleague here is asking if we are considering the policies of the teammates in the POMDPs. So what we do here is we're not solving decentralized POMDPs. We are considering, first of all, multi-agent Markov decision problems. We consider the policies of the teammates, and we reduce the transition probabilities using the policies. So we do use the law of total probability, and we consider that for each MMDP and for each teammate, we have the transition probabilities of our agent, because since we do not control the policies of the teammates, they can be considered. So we reduce the multi-agent Markov decision problem to a simple MDP. And then we add the partial observability on top of the MDP. So we are solving a POMDP instead of a decentralized POMDP, which is much simpler.
Okay, thanks.
Does it make sense? Okay. Was this clear to everyone at home? Perfect.
Okay, we thanks João again. And we're gonna move on, I guess. The next one is online. So we'll have here. Well, I'm gonna stop the share and I'm gonna ask Arash if you can unmute yourself and share your screen.
Yes, Ignacio. Just hang on a second.
Yeah, no worries.
Okay. Can you see my screen now?
Yes.
Okay. Hi, everyone. So today I'm going to present our recent work that is addressing how to make a more robust ad hoc teamwork agent by creating diverse training teammate types. Now, this work was jointly done together with Elliot, Ignacio, and Stefano, which are also the organizers of this workshop. And yeah, so before I go into our approach in order to make a robust ad hoc teamwork agent, I'll just like briefly recap what the ad hoc teamwork problem is. And it's actually something that has been mentioned also in the previous presentation, but basically ad hoc teamwork is this decision-making problem where we assume control over a single agent, which we call the learner. And this learner must learn to achieve a specific goal in the presence of other agents without using any prior coordination mechanisms, such as joint training or maybe pre-specified communication protocols. Now, for an example of an ad hoc teamwork problem, let's just think about this example where we try to design a robot that needs to interact with other robots inside a pickup robot soccer game. In this particular case, this robot might need to collaborate with other robots that uses different policies in order to decide how they act in this particular robot soccer game. Now, as a brief recap, previous works that solve ad hoc teamwork, most of them are based on this approach called type-based ad hoc teamwork. And this is also similar with how the previous presentation solved ad hoc teamwork. Basically, in type-based ad hoc teamwork, we try to observe the teammate behavior, and based on how teammates behave according to our actions, we update our beliefs regarding them. So we update our belief about how about their types, their decision-making processes. We update, and based on that, we then decide how we should interact with them. So basically, our belief regarding how teammates are going to act, that's going to inform how we choose our actions in the future. Now, to borrow like a visualization from Sam Barrett's work, basically, in general, this is how type-based ad hoc teamwork goes. So essentially, at each time step, like I mentioned, an agent will observe the state information, which contains some information about how teammates behave in the environment. And based on that, it updates the belief on the behaviors of the teammate, what they're going to do in the future. And that is going to inform basically how our ad hoc agent is going to behave in the environment. Now, notice that most importantly, the way the ad hoc agent updates its belief regarding how teammates will behave, that's mostly going to be dependent on knowledge that it has during training. And this knowledge could be like hand-coded prior knowledge that is provided by an expert to the agent, or it could be just knowledge based from interacting with other teammates during training. And you can see this in these two different sources of knowledges here in these rectangles above. Now, under this specific kind of setup, ad hoc teamwork learning faces this particular challenge when it comes to type-based ad hoc teamwork methods. In particular, when it comes to the learned knowledge that you obtain by interacting with teammates during training, it is necessary for you to have training teammates whose behavior resembles the teammates that you're going to encounter during evaluation. If you don't have this kind of training teammates beforehand during training, there is always a risk that the knowledge that you learn during training is not going to be that useful when being applied to interaction with teammates with, previously unobserved behavior during interaction. Now, this in itself is going to be some limitation for ad hoc teamwork training, because in many realistic applications, sometimes it is actually pretty hard to supply training teammates that you could use to inform the training process for ad hoc teamwork. And this is something that I personally have experienced during my research in ad hoc teamwork. Sometimes it's not so clear what kind of teammates should I use in order to train my agents during the training process. Now, our work tries to answer this question. So how can we actually discover training teammate types such that eventually, if the learner is trained on these training teammate types, it becomes robust to any kinds of teammate behavior that it sees during interaction. So in essence, unlike the usual ad hoc teamwork setup where we try to optimize for an ad hoc teamwork agent, how it learns so that it could effectively collaborate with others, in this work, we're trying to optimize for the teammate training set. So we try to optimize for the set of teammate behaviors that is encountered during training, and how would we design it such that it becomes useful later in terms of making the agents more robust during evaluation. Now, this is one idea that we had. Basically, the idea is we could improve the robustness of an agent if we somehow create a set of teammates that are diverse in terms of their behavior. Now, the reason why we do this is because we will then hope that the learner will eventually learn to adopt a wider range of behavior to deal with teammates. So, as an example, in a football example, let's say you create agents that have an attacking style and also a defensive style. If you create agents with two different playing styles like this, the learner, the ad hoc agent that you're training, would eventually learn how to complement both these two playing styles. So if it is interacting with an attacking player, it will then probably try to assume a more defensive role, so that the team becomes more balanced. On the other hand, if it is interacting with a defensive teammate, it will try to be more offensive to add more goals to the team. Now, the problem now here is that, okay, if diversity is what we want from our set of teammates during training, how do we define that diversity such that it eventually forces the learner to eventually learn a wider range of behaviors during training? Now, one observation that we made is that such diversity ideally cannot be based on teammate trajectory, because teammate trajectory alone does not actually necessitate different responses from learner. So basically what I'm saying, there are many different trajectories or sequences of actions that that a teammate could execute, which eventually requires the same best response by the learning agent. And if that's the case, it doesn't actually force the learning agent to acquire a wider range of behaviors. As an example of this, consider this simple environment where essentially you have two agents, the ad hoc agent and another teammate. So the ad hoc agent is like the square here, with brighter red. And basically agents in this environment, they will be rewarded if both agents just move towards like these two circles, but they need to move to the same circle. Under this particular scenario, there's basically like two solutions, right? Like either both of these agents go to the bottom right corner, or they go to the upper left corner. Now, under trajectory diversity or like sequence of action diversity, we could actually see these kind of example where we don't actually generate diverse behaviors. So let's say we generate two agents with diverse trajectories. So these two teammates here, both the parallelogram of this like flag-like symbol, they correspond to the teammates that we generate. Now these teammates displays this trajectory. Yeah.
Rush, you have 2 more minutes.
Oh, okay. Sure. So these two teammates display this trajectory that is displayed by the arrows here, and you see that both actually display diverse trajectories. But essentially, the best response that the learner needs to do when dealing with these two behaviors is to just go to the bottom right corner here. And because of that, the learner does not actually acquire this important behavior of going to the upper left corner if the training set of teammates is something like this. Now, on the other hand, I think what we want is diverse. What we actually want in terms of diversity is diversity in terms of best response. So the question is, how do we actually force this diversity is such that it necessitates the learner to learn different policies that are incompatible with each other. So as an example here, we have an example. Let's say if instead of creating a second teammate that also goes to the bottom right corner, it goes to the upper left corner. Now, under this particular case, the best response of the learner is not longer going to be going to the bottom right corner, because that alone will not be good enough in order to interact with his teammate. And if that's the case, this will eventually force the learner to acquire a behavior that goes to the upper left corner. Now, since we're running out of time, basically we have like a mathematical approach to kind of optimize this, but our approach enables us to optimize this end-to-end using multi-agent reinforcement learning. And we kind of basically add this diversity metric that we include in the usual multi-agent reinforcement learning objective. And based on that, we essentially, at least in this particular simple environment, we are able of actually learning these two diverse behavior that I mentioned, where essentially each teammate will then discover the two different ways of optimally behaving in this particular environment. On the other hand, with trajectory diversity, although it's not always the case, there are some runs where teammates will end up going to the same corner, and the learner will not acquire a behavior that goes to the other corner. Now, with future work, our plan is to kind of expand this diversity metric that we have into others and test like other alternative ones. We also want to evaluate it in more complex environments. And yeah, essentially, that's pretty much it.
Thanks, Arash. Really interesting work. And we have time for one question. I don't know if anyone here has one or someone online.
I have a question.
Mm-hmm.
So thank you. It's really interesting work. So you talked about diversity. Do you think you can use other techniques for diversity from, I don't know, maybe supervised learning, or diversity is something that people have been looking at recently, with a slightly different meaning, but maybe it is something that you can somehow import into this work.
Well, to answer that, basically, absolutely. Basically, even our techniques that we use at the moment, they're actually inspired by diversity metrics that are previously used in other areas of machine learning. So the only thing that I think I need to emphasize here is that we need to really carefully define this diversity, because as I mentioned earlier, there are some definitions of diversity, as an example, trajectory or sequence of action diversity, which don't always imply that doesn't always cause the learner to acquire the interesting behaviors that are required for robustness. On the other hand, I think even in our case, we actually are trying to explore like 3 other diversity metrics apart from the ones that we are proposing today. But essentially, there are so many other diversity metrics out there. But we think the most important takeaway here is that these diversity metrics should all be based on best response diversity, because best response diversity forces the learner to acquire the different best responses that are useful in interacting with agents in that particular world.
Great, thank you.
Okay, perfect. Thanks, Arash. It was a great presentation. Now let's move on. And Ram, are you ready? Perfect. Just go ahead and share your screen when you're ready. I'll let you know 2 minutes before 10 so that we can keep it on schedule.
Great. My screen is visible?
Yeah, we can see it.
Awesome. Okay. Hi, everybody. My name is Ram. Thanks for coming to my talk. This is actually my first time speaking any kind of academic conference. So I'm not an academic. I'm a software engineer trying to do a career change and work on multi-agent RL research full time. So this is gonna be pretty basic. I hope it's still gonna be interesting to you. Oh, and thanks to Owen Milski for helping me figure out how to present my experiments in this conference. So anyway, my talk is going to be about a series of experiments that I'm running and trying to set up implicit communication between RL agents. Yeah, I've got 3 links here for the slides, for the paper, and for the code. My goal with the research, my ultimate goal is to use a multi-agent RL to model human society and understand it better. Basically, have a setup where I have an environment with a bunch of RL agents. And the RL agents are interacting with each other in a way that's somewhat similar to the way that people interact with each other in the real world. So looking at other research tries to do that. One piece we're missing is emergent reciprocity in learning agents, where they have social dilemmas with each other. And my direction is, I'm thinking that if I have experiments where the agents are learning to communicate with each other in an emergent way, this might lead somehow to emergent reciprocity. So the experiments I'm going to show today is one of my attempts to get the agents sort of feel each other in the same environment in an emergent way. You can read more about my research and my goals on that link. So my goal for these experiments that I'm going to show now is to have an environment where the agents learn a communication protocol on the fly and the communication is implicit, right? This is the opposite from the communication we've seen in Carlucho's talk, which was explicit. In Carlucho's talk, each agent was sending a message. It was a chip talk channel. It was sending a message to the other agent. Like sending message was an on-tick part of the game, where I want to go for the opposite. Yeah, I want to have a setup where the agents are moving around the world and doing whatever is good for them, like eating food, and their actions, their movements are implicitly sending a message to the other agents. And I want agents to both understand how to send these messages and how to receive them without having it too coerced. I want it to be an emergent behavior. So I made up a game with game rules, and I'm going to explain the game rules, and then I'm going to show you how the agents behave on these game rules. So these are the basics. The game is called Fruit Slots. And we have 2 agents, and each of them are moving between 10 slots. The first agent, marked with 1, is on the top row, and he's traveling between the 10 slots in that row. And the second agent, shown as 2, is on the bottom row, and it's traveling between the 10 slots. On each turn, each agent chooses which slot to go to next. I mean, in a way, it's similar to a multi-arm bandit problem. Each agent chooses which slot to go to next. If there is a fruit in that slot, it consumes the fruit. More details about the fruits and the rewards for them later. And each agent can see the movement of the other agent and the location of the other agent. So let's look at the first experiment. In the first experiment, once in 5 turns, I introduce a pair of apples into the game. And I put the apples in 2 opposing slots. If an agent eats an apple, it gets 1 point. And the trick is, I only tell one of the agents that I've placed apples in a specific pair of slots. So in this case, agent 1 sees that there is an apple for it in slot 7. But agent 2 doesn't see anything. Agent 2 just sees blank rows, and he just sees the location of agent 1. Now, my goal with this experiment, first, I want to see that the agents are eating the apples that they see, which is straightforward. And then I want to see them eating the apples that they don't see. My thinking is, if I'm agent 2 and I'm seeing agent 1 going to slot 7 and eating an apple there, so I'm thinking, I mean, I'm seeing agent 1 going to slot 7 and I'm not seeing an apple. I'm just seeing agent 1 going there. So I'd be thinking, maybe there's an apple there. Maybe I should go to my slot 7 because maybe there's an apple there. In worst case scenario, it's not like I had anything better to do, so I'm not really losing anything. So I want to see a behavior where the agents are constantly learning to imitate each other, just because it pays off for them. I ran this experiment and it worked like I expected it to. The blue line in this graph shows the agents learning to eat the visible apples, which happens very quickly. It's not very challenging. And the red line shows how well they are eating the invisible apples. And as you could expect, the rise in the is the performance of the invisible apples only comes after the performance of the visible apples. So they learn to imitate each other only once they are good enough to imitate, only once there is something worthwhile to imitate. So I like the way that the behaviors are stacked up on top of each other, and I want to stack up more behaviors. I make it an autocurriculum. So here's a second experiment. Once in every 25 turns, I introduce a banana. There is only one banana, not two, and I put it in a random slot either in the top row or the bottom row. And here's how bananas work. If an agent eats a banana, both agents, each of them gets 5 points. Doesn't matter who is the one who ate the banana. But the agent on the banana side can't see the banana, and only the agent on the other side from the banana can see the banana. The thing I want to see here is I want agent 2 to see the banana and sort of have this thought that I want agent 1 to eat the banana. So I'm going to go to slot 3, to my slot 3, the bottom slot 3, and I want agent 1 to imitate me, and then go to the top slot 3, and then eat the banana. Right? So we are sort of counting on agent 2 sending the message and agent 1 receiving the message, even though I haven't explicitly incentivized them to be sending or receiving messages. I want that as a sort of like emergent behavior over the fact that they just like to eat fruit. I ran this experiment, and I was happy to see the results. There is a climb in the performance of eating banana just after they learn to imitate each other, because the way they signal to each other to eat the banana has to rely on the fact that the other one is imitating them. Okay, so that's pretty cool. And then I want to stack another layer on top of that. So this is going to be the most complicated one yet. I'm going to explain it, and spoiler alert, it didn't work the way I wanted to, but still I'm going to explain what I tried to do here. So once every 100 turns, I introduce a banana and 5 lemons. The banana is governed by the same rules as the previous banana, right? If one of the agents eats it, then both agents get 5 points. But the lemons, so the lemons are only visible for the agent that's on the other side from the lemons. So in this case, agent 1 sees the lemons, but not the banana, and agent 2 sees the banana, but not the lemons. So as far as agent 2 is concerned, he doesn't even know it's a lemon turn. He might think it's just a banana turn this time. If agent 2 eats a lemon, agent 1 loses 20 points. So agent 1 really wants agent 2 to not eat the lemons at all. And like, this is much more important to it than the banana. And the behavior I want to see here is that agent 2 goes to the bottom slot 3 to signal to agent 1 to eat the banana. And then I want agent 1 to intentionally not eat the banana, just so agent 2 will stay in the same spot. Because if agent 1 will eat the banana, then maybe agent 2 is going to wander off and go to eat the lemons by mistake. So I ran this experiment, and I'm not happy with this result, because I'm seeing a climb in the performance of lemons, and I'm seeing that climb way too early. I mean, I'm seeing it even before they learn to imitate each other. So I'm not sure exactly how they figured out how they managed to beat the lemons. One hypothesis that I have is that I use pairing zoo and stable baselines 3 to run this experiment, and the way they work is they have the agents share the same neural network, like they share the same weights, and I suspect that this may have tempered the results, make it easier for the agents. It's also possible it tempered the results of the previous experiment that I've shown earlier. So my next goals for the research is, one, I want to learn RLib and figure out how to run this experiment with each agent having its own neural network weights, and see whether that changes the result. And I want to design a few more similar game domains where the agents are constantly incentivized implicitly for listening to each other and for sending messages to each other. And I hope that if I can do a bunch of these experiments and get a better intuition for what happens there, this could help me figure out emergent reciprocity. So that's it for me. If you want to get updates on my research, I'll put a link here for my mail list. I send an update once every month. I'll be happy to get any questions. Thank you very much.
Thanks, Ron. Really interesting work. Also interesting that you come in not from the academia sector. You in the Python Foundation, is that correct?
Yeah, yes.
That's really interesting, I guess. Okay, so let's move to questions. I don't know if anyone here has questions for or anyone online. Yeah.
I'm interested whether, so do you use recurrent policies for this, or is it like something fully connected?
I can't hear you. So
Yeah, I can repeat. He's asking if you're using recurrent neural net policies or it's just fully for nets.
no, I use PPO. I think PPO isn't recurrent, right?
I mean, yeah, I guess you can choose to implement the networks as
Recurrent.
Yeah, you can use PPO with recurrent policies, but
I don't think it's specified recurrent for the PPO.
okay.
Okay.
It might be interesting to see whether, because it seems some of this kind of behavior might rely on remembering what agents have been in the past as well, or at least you might get some interesting behaviors that agents can remember the history of interactions instead of just the current state of the world.
I don't know if you could hear that, but
Yes, I can, and I agree.
Yeah.
Yes, if they would have a memory, it might be different. Like right now, every turn they have completely no context for what happened before. Like they can't
Exactly.
even like count turns and stuff like that.
Yeah. And I have a question. From your results, seems that you were only testing this for individual fruits, right? You're not combining them into one single like environment. You were seeing these at different environments, basically.
No, I know it's confusing. Like a bunch of people asked me about this in the past. Like whenever they play the game, like once every 5 turns I show them the apple, and once every 25 turns I show them the banana, and once every 100 turns I do the lemons, and it's all in one game. It's just I'm doing a frequency of the more high point targets lower, so there will be some kind of balance between them.
Oh, okay, I see. Yeah. I don't know. Someone else has questions? I think we're on time, so we're gonna move on, and no one has questions. I don't know if anyone online has anything.
Alicia has a question, but she's muted, or we can hear her.
Oh, I cannot see her. Oh, I cannot hear you, Alicia.
Yeah.
Maybe you can type it, if not.
I message her.
Oh, okay. Okay.
But just that's fine. Okay.
Oh, yeah, she's just not playing. Okay, that's fine. Then we can move on in that case. Thanks again, Ram, for your presentation. So in this case, we're moving on. We're gonna go back to in person. It's Elias' turn now to present. Let me open this one. And I'm just gonna move away and just leave the room to Elliot that is gonna present his work. Good? Okay. You can just share a screen.
Okay.
I didn't share the screen for you.
Oh, okay.
Okay.
Okay. Maybe we should check this. I hope every image shows up in the presentation. Okay.
We see the presenter's mode.
Oh, really? I see the non-presenters mode, which is kind of annoying, I suppose. How do you? Is there a way you can do it without the presenters mode?
Click on the Use Presenter view. In the monitors.
Something always goes wrong with the.
Yeah, it seems like we broke the microphone. Can you hear us, guys?
Yes.
Okay.
Okay.
Oh wait, why is this? I don't know why this thing broke. You just do it like this, Elliot.
Yeah, isn't that like just go and take the user presenter view book and then okay.
Yeah.
Yeah.
You take that one. Yeah.
Okay. Okay. This should
That
be
will
right.
work.
Yep. Okay. Great. So I'm going to present today some work on Few-Shot Teamwork, which is a project that I've been doing with Arrasy and Ignacio and also Stefano. So yeah, let's get straight to it. Okay. It looks like there's some rendering issues here, but hopefully it doesn't end up too bad. Okay, so did it two separate problems. The first is training a team to complete a complex task. So, for example, five-a-side football. It's quite complex, and there's a couple of challenges that can be introduced when trying to train agents to complete this. So some of these issues include non-stationarity, policy search, multi-agent credit assignment. So which of the agents contributed to obtaining the reward, and difficulties with coordinated exploration. A possible solution to this could be a curriculum-based approach. So the idea here is, consider you were, say, a football manager, and you wanted to train your team to play five-a-side football. Instead of throwing them in at the deep end and trying to learn to play five-a-side football from the start. Okay, this is kind of a problem. I think the rendering is kind of messed up. I could try to quickly send.
Just keep going, I guess, with like this.
Okay, the only thing is, I think it's going to get quite bad in other slides. So yeah, I think I really need to. I will just be a second. I will just. We probably should have checked this before.
Yeah, we have some rendering issues because he did his presentation in Linux and we're on Windows now.
You should stop sharing. I will send you a version on Discord.
Yeah, so just a few minutes, guys. Just to update everyone, though, we're moving the schedule a little bit later, so we're gonna start a little bit later. We're gonna have 1 hour to have lunch, so it's gonna be fine. So as soon as we finish this, we'll just take an hour break for lunch. So no worries, we're still gonna be on time. And sorry about this, Ruth, I cannot hear you.
Yeah, is it hour for lunch or just pushing 15 minutes and like it's because now it's 12:15 or almost 12:15.
We can also just take the lunch now and then we put Elliot presentation in the second session if you want to do that.
It's okay. I mean, I think I can send you this right now.
Okay, yeah. On Discord?
Oh.
Yeah, okay. Whoops. Well, everyone's checking my screen, but it's worked Discord, so it's fine. But yeah, so let's just do this one, I guess, and then we move on. We have 1 hour though for the other session, so we should be right on time. We should be fine.
Yeah.
Okay, yeah, I haven't got it yet. Yeah.
Sorry, I sent it in not directly. I sent it in
this.
Yeah.
Okay, the PDF.
Can you put the PowerPoint one in there as well? Because I have animations. If it doesn't, like, if it hasn't broken the rendering, then use that. Okay. Can you?
That's fine, right? Yeah.
Can you run from the first slide?
Yeah, this.
Can you run it? We can just
Oh yeah. But let me share a screen. Okay.
Okay, right. Okay, sorry about that. Okay, so just a couple of issues. So, okay, so if you were managing the five-side football team, instead, what you might do is consider training your agents separately in smaller versions of the game. So, for example, you might train some defenders with the red team here to play in a kind of defensive task where there are only two agents. So, credit assignment becomes easier, and the space of to search and policy is probably easier. You do a similar thing for attack drills to train some attackers. Once you have these trained separately, you can then bring them together in the five-a-side football task and try to kind of then focus on getting them to learn to work together while still retaining the skills that they learned during the drills. So that's problem one. And an alternative problem, which is kind of similar to ad hoc teamwork areas, collaborating with unfamiliar agents on a new task. Let's say instead of having access to the training academy, we simply got, as a manager, we simply agents who are trained to be attackers and trained to be defenders. And it's our job to get these guys to work together and actually learn to play five-a-side football. So they already have the skills. We didn't have any control over how they were trained in that case, but we do have control on, okay, how do they learn to adapt to each other? So some of the challenges there, for example, we want to achieve rapid mutual adaptation here. We might consider trying to model the other agents, and we want to learn to play five-a-side football very efficiently. So this is essentially an ad hoc teamwork. So my claim is that these two problems, and you could probably tell from the diagrams, are very related. And I kind of put this under the umbrella of few-shot teamwork. And so I'll just discuss a bit what that is. So to formalize few-shot teamwork, we consider two stages. So I'm going to kind of carry on with the example of the football task. So we start with a source stage where agents are trained with respect to some possibly simpler source tasks. So here we label them task 1 and 2. And they're trained convergence in these. And so the agents are pre-skilled with respect to the source tasks. So the output of the source task training stages are teams of skilled agents, P1 and P2. We then combine these teams and we train them on our target task. The target task is the task that we want to solve, which in this case is five-side football. And so we have an adjustment stage, which is where a new team formed of the individual sub-teams gets some trial runs to adjust to its new task, and name adjustment stage. So our overall goal here really is that so in the one setting, we would want this whole pipeline to be much faster it would take to train from scratch in five-a-side football. So to dig in a little bit deeper, in general, we could have up to M different source tasks. Each one puts a trained team, so P1 through M. So we make some assumptions such as each source task is independent and unaware of the other source task. So agents trained in task 1 aren't aware of the agents being trained in task 2 at this point in time. And they're also not aware of the next task that's coming up. So this is kind of a restrictive assumption that we could relax. But, it's one that we make for now. So in each one of these source tasks, we apply the same learning algorithm, less for source. And each one, so the EMP source task trained for N SM training steps. This learning algorithm outputs various things, for example, skilled policies for each teammate. We could also output other stuff as well, for example, value functions from the source tasks or buffers of experience in the source task. And this might be useful in the next stage, in the adjustment stage, because, for example, they might be useful to kind of compare experiences in the target task to experiences from the source stage. So things like experience buffers might be useful. And then in the adjustment stage, we combine the teams And then, so I've said like in the general case, the new team could be like, you could pick agents from each subtask, each source task. You don't necessarily need to combine all of them, but you could just select a few from each. So this is why there's the subset operator there. And essentially, we bring together the agents from the subteams, we train them on the target task T. Instead of using the source stage learning algorithm, we apply the adjustment stage learning algorithm. And we train for NA training steps. We evaluate, and our kind of overall target here is to maximize the performance on the target task. So as I said, we want to maximize the mean episodic return on that task. So assuming that we have a target performance, G target, like a bullseye, I guess, and that's reached by a baseline algorithm in n target steps. So if we apply standard RL methods, it takes n target steps to reach our goal of G target. We can interpret the two problems that I discussed earlier, problem 1 and problem 2, by considering the training requirements. So problem 1 was the problem of training a team to complete a complex task. In this case, what we want here is that the total number of steps should be, training steps should be much less than baseline RL algorithm. So the adjustment stage steps plus the sum of the source stage steps should be much less than the target. So we are much more efficient than kind of standard mod techniques. In problem 2, what we want is we don't really care about how long the agents are trained for the source tasks. What we care about is that we have very rapid adaptation during the adjustment stage. So I've kind of represented this by saying like this a number of steps in the adjustment stage should be like ideally approaching 0. So our kind of targets for optimization in the few shot teamwork problem are the learning algorithms. So what we're trying to do is design learning algorithms, LA and LS, which achieve these conditions. So the couple of assumptions we make, one is the independence of tasks, as I mentioned before, but we could relax that. We assume that the source and target tasks are given. So you could imagine the kind of procedure I described in problem 1 as a kind of curriculum approach. So it's a curriculum approach to multi-agent reinforcement learning. And lots of work on curriculum learning focuses on actually learning which tasks should I use for my curriculum. This isn't our problem. Our problem is, given that we already know what tasks are in the curriculum, how do we quickly adapt during this curriculum? So just wanted to make the distinction between the two. And another important thing is that we assume an exploitable relationship between the source and the target task. And this is something that I think is important to note, because, so I would just say a couple of words on this. So we wouldn't expect in general a solution for arbitrarily different source and target tasks. It would seem like unrealistic that for any given source task, we can find an algorithm that would allow for rapid adaptation in a target task. The source task could be completely unrelated to the target task, and in which case there isn't really any kind of information there. I mean, this is usually like formalized via no-free lunch theorems. So we need some kind of relationship between these tasks. So we formalize this intuition, and I have like an idea called the useful skills formulation, and the idea is that the relationship between the tasks should be such that agents from the source tasks should be skills learned in the source task should be useful in the target task. So for some set of states in the target task, the policies from the source tasks should be optimal in some of these. So I operationalize this by domains of expertise, something I call domains of expertise. So domain of expertise was for a subteam P is a set of states for which P's policy from the source stage is optimal in the new task. So just to give an example of this, consider the football game. We have the subtask attack rules and defense rules. So if you consider this football field here, notice that the enemy team, the green team, has the ball and is about to shoot on goal. This looks very much like something that the defenders saw during their source task. So their policy from the source task, in this case, is probably optimal. Therefore, we say that this state is in the defender's domain of expertise. So this whole like box here is the state space of the target task, and within that, state falls into there. Now, for the attackers, there's a similar domain of expertise. So this is like an attack scenario from attacking skills. So this goes in the attacker's domain of expertise. Then there are some states where the optimal behavior has never been seen by either source. For example, the defenders don't know that they need to pass the ball to the attackers because during defense rules, they never had to do this. So this state here where the optimal policy is for the defender to pass the ball to the attacker so they can shoot is the optimal policy. But that was never seen in either source task. So I put this in kind of the outside space, which I call the coordination space. And these are the set of states where the agents need to learn new information about the new task to coordinate. So we've been working towards a solution for few-shot teamwork. And my hypothesis at the moment is that the learning algorithm ought to focus on the regions where agents need to coordinate to explore the new task. That is these regions outside here where neither of the agents have seen any kind of experience before. So the agents where the scenarios where both agents are already good, or both sub-teams are already good. We don't need to do anything there. We should avoid these states. We already know how to work well there. We don't need to make any updates. Just ignore that. It's kind of inefficient. We should focus on states where we need to learn new behavior. So we want to focus on exploration in these areas. And in these areas, not in the intersection, only like half of the team needs to explore. The other team should not explore in order to reduce non-stationarity towards the other agent. So the hypothesis is we ought to focus on regions where the agents need to coordinate to explore the new task. So we've tried a couple of approaches so far, but they were fairly simple and none of them really seem to have outperformed baseline so far. But, we're investigating some, I think, fairly promising ideas, which are still at the early stages, but I think hopefully we'll get some good results soon and something that actually works because, yeah, I think it's an interesting problem and I hope to make some real progress on this. So that's all. Thanks for listening. If anyone is interested in the workshop paper, my personal website or group website, QR codes are up. And yeah,
That's a good idea.
That's all. Thanks.
Thanks, Elliot.
And I guess we're just gonna skip the Q&A. I mean, we can talk during lunch, but being 12:30, we're just gonna go ahead and go for lunch here. And we meet here